A protection zone is the area covered by a single protection system. Here we have a typical two-ended feeder circuit. The protection for this feeder uses current transformers at each end of the feeder, adjacent to the circuit breakers. The area in between the current transformers is defined as the protection zone, and this defines the outer boundaries between which the feeder protection will operate. Let's now close the circuit breakers, energizing the feeder. If a fault occurs in between the current transformers, this is classed as an in-zone fault. Because it's an in-zone fault, the feeder protection will operate, tripping the circuit breakers at both ends of the feeder, clearing the fault from the system. Let's now clear the fault. Here we have a fault at end B. This is not within the defined boundaries of the protection zone and is classed as an out-of-zone fault. Because it's not within the defined zone, the feeder protection won't take any action. Let's now clear the fault. What about a fault in between the feeder circuit breaker and the current transformers? Well, as we can see, it's outside the boundaries of the defined protection zone, but it's still on the feeder and needs to be cleared. This type of fault is called a short stub fault and is one of the issues that we need to overcome when we define protection zones. To ensure that we monitor 100% of the electrical system, we normally try and overlap protection zones. There are two classic ways of doing this. The first option is to put current transformers on both sides of the circuit breaker. We connect the right-hand current transformer to the first protection zone and the left-hand current transformer to the second protection zone. We have now formed an overlap so that the conductor in between the circuit breaker and current transformer is protected by one of the two zones and is therefore being continuously monitored. The second option is to have two current transformers on the same side of the breaker. We then follow the same principle and have the right-hand current transformer connected to zone 1 and the left-hand current transformer connected to zone 2. Again, the two zones overlap and we protect 100% of the conductor. Having short stub areas is unavoidable on transmission level networks if we want to provide protection zones to cover 100% of the electrical network. The alternative would be to provide areas that have no high-speed protection, which is obviously not acceptable. The chances of a fault on the 2 meters of busbar in between the current transformer and the circuit breaker are obviously minimal, and most designers accept that a short stub fault risk is worth taking for the benefit of covering 100% of the busbar. Let's now see how we would use the protection zones when the current transformers are both on one side of the circuit breaker. Here we have a typical transmission network with two ends. Firstly, let's look at the feeder protection. As we can see, the maximum coverage that we can provide are the two outermost CTs. This therefore forms the feeder protection zone. Next, let's do our busbar protection zones. To provide an overlap, again, we choose the current transformers farthest away from the busbar. So let's do the zone for end A and end B. Again, with this arrangement, we've protected every single piece of conductor. Let's now close the circuit breakers and see what happens under different fault scenarios. Current will now flow from end A through the feeder and on to end B. Let's now apply a fault on the busbar at end A. As this is a transmission system, we will get current flowing into the fault through incomers A, B and C, and are also likely to get current back feeding into the fault through the feeder from MB. The fault is within the busbar protection zone, which will then detect the current imbalance and trip all of the circuit breakers connected to the end A busbar. the fault has now been disconnected from the system, and everything has worked as expected. Let's now remove the fault. Let's now add a fault on the feeder. This time, current will feed into the fault from both ends of the feeder, causing a large current imbalance which will be detected by the feeder protection, which will then trip the circuit breakers on both ends of the feeder, disconnecting the fault from the electrical system. Let's now clear the fault. Let's now see what happens if we get a short stub fault in between the circuit breaker and the current transformers. Again, you will get current flowing into the fault from the incomers on end A and current backfeeding into the fault through the feeder from end B. But which protection system will operate? Well, the fault is inside the busbar protection zone, but not in the feeder protection zone. Therefore, the busbar protection will operate, tripping all of the circuit breakers connected to the busbar. But this has not disconnected the fault from the electrical network, as we're still getting a fault contribution through the feeder from end B. This is the main issue that we face in putting the current transformers on only one side of the circuit breaker, as this stops us using the protection zones to detect a short stub fault, which is why most electrical utilities try and put the current transformers on both sides of the circuit breaker. Let's now look at the same system, but this time put current transformers on both sides of the circuit breaker. This time we can cover 100% of the conductor in between the circuit breakers by using the outermost current transformers. Again, for the busbar protection, we use the current transformers farthest away from the busbar to provide the largest protection zone available. Let's now close the circuit breakers and see what happens this time with a short stub fault. Again, the fault current is fed from both ends, but this time the fault is located in both the busbar protection and feeder protection zones. Therefore, the busbar protection operates and the feeder protection operates, closing down the whole network. Using protection zones formed by the current transformers allows us to provide a simple way of locating any fault that may occur on the network, and make sure that we only trip the minimum amount of the network necessary to clear the fault, i.e., achieve good fault discrimination.